Okay, today's topic is actually on work, energy, and power. So this is just an overview, as well as later on I think there will be another video that talks about how do you use conservation of energy, specifically the principle of conservation of energy, and how do you actually use all the different formulas involved. So in this overview, we actually talk about the fact that work is viewed as energy is viewed as the capacity to do work. So energy is related to work, and power is the rate of work done. So the rate of energy used, the rate of work being done, okay, energy conversion and things like that. So that's how you have power, and energy is required to do work. So energy is the capacity to do work. So next we then ask, so what exactly is work? So to understand that, actually the easiest way is to look at the formula or the definition. Work is considered to be done when there's a constant force that produces a motion, and the motion is in the direction of the force. So you notice that I'm placing a parallel sign. The parallel sign is to indicate that the direction must be in the direction of the force. Okay, so for example, if I talk about a box over here, I have a force towards the right. The distance moved must be parallel to the force. Okay, only then when we multiply these two factors together, the product will give us what we call work done. And work done is actually a way in which we calculate the energy that we use. Notice I use inverted commas. It means that you are not supposed to say calculate. In the definition, if you're asked, you have to say it's the capacity to do work. Okay, so when we say calculate is, you see, scientists want to know how much energy we need to do certain things. For example, to drive a car, to move an object from one place to another place. So work done is a concept that they created, they come up with to calculate and determine how much energy is actually required. Yeah, so this is what work done is about. So when we do work, if I'm the person here pushing the box, then when I push the box using this amount of force F across a distance parallel to the direction of the force, I have actually used a certain amount of energy, and that amount of energy is actually transferred to this box. Okay, it's actually transferred to this box. So the box will have gained energy. Now this is of course ideal situation where we assume there is no friction on the ground. Right? We assume that there's no friction on the ground. What happens if there is? Then that's where we so-called lose energy, right? Some parts of the energy that we use in doing the work, in pushing the box, will be used to overcome the frictional force, overcome resistance. And so that means that the box will actually gain less energy. Okay? So then this on to the next part, in which we talk about the fact that by the principle of conservation of energy, we realize that there are actually three important components, but in your textbook we only focus on two. The first one is energy is neither created nor destroyed. So if it's neither created nor destroyed, the energy must come from somewhere, and when it has to go to somewhere else, and it cannot just disappear. Okay, so where did it go to? That's where the second part will come in. We talk about the fact that it can be converted from one form to another form. Okay, so when it's converted from one form to another form, we are looking at things like, for example, conversion from, say, GPE to KE, gravitational potential energy to kinetic energy, from chemical potential energy to gravitational potential energy, and so on and so forth. The third one that is actually not inside your textbook is actually the fact that it can be transferred from one object to another object. Transferred from one object to another object. Okay, so refer to the previous example when I said that I do work on the box and actually transferring energy from myself to the box. And when I'm transferring energy to the box, if there is friction on the ground, I'm also transferring energy to the ground in the form of heat, because work done against friction is usually dissipated as heat. So right now let's talk about power. What then is power? So power, as we mentioned earlier, is actually the rate of work done. So it's actually the change in energy over the time taken. Now we realize that the change in energy is actually the same as the amount of work we do. So work done over time. So this is the same. So in short form, we will usually just write P equals to E over T. And so if I want to find out energy equals to P times T as well. So all these are different ways of showing the formula. When we move on to electricity, you realize that when you go on to Sec 4 or 5, we learn about electricity. You realize that energy can be expressed in terms of V times I times T in terms of electricity, because these two gives you what we call electrical power. Okay, so right now this is not useful for you. Okay, so let's carry on with that. With this, when we talk about power, the unit, the SI unit for power is actually watts, capital W. Okay, and you know that power, the units that you need to use for work done, the SI unit is joules. So actually 1 watt is equals to 1 joule over 1 second. So whenever you're using this formula, remember to convert the unit into seconds. Alright, so with that, more or less we are done with this chapter, the big idea of this chapter. Another thing that you probably need to understand is this thing called efficiency. So efficiency actually talks about the useful output power over the total input power, and is usually expressed in percentages, so it's times 100%. Okay, so this equation will then be useful if you actually ask about how effective or how efficient is a machine. Okay, assuming let's say you give a machine 100 joules of energy, how much work can it do? So that the work that it can do is actually known as your output power. Okay, dependent on the time, of course. So your useful output power over your total input power will then give you the efficiency of a machine or an object doing work.